Remember?
It's very long.
Approximation for CP channels. Should we see Mark?
Oh yeah, it's just.
So it's a pleasure to welcome Marco Michel from Singapore to give this talk. It's called Non-Asymptotic Fundamental Limits and Gaussian Approximation for Classical Quantum Channels.
Thank you very much. Thank you very much. And now I know why you needed me to write down the title. Yeah, it's a pleasure to give a talk here. So, what I will talk about is classical quantum channels, which is maybe the first channel model that has been studied in the quantum domain. So it's just a map from a finite alphabet to states on a finite dimensional Hilbert space. So this map is given by a mapping like this. Okay, and now what I'm interested in is something very similar than what Mark has been talking about last week. So I'll start with the graph that he had, where this is the rate at which we send information over the channel, and on this axis we have the error. So here is 1 and here is 0. Now what Mark was trying to prove last time is that for certain channels
Probability of error?
yes. For certain channels there is a sharp transition at the capacity. So we have probability of error being 0 below capacity and being 1 above capacity. And now this is a very nice result, but it's also a bit boring, because this is just a step function now. And the question is there something more to that? So here, kind of for this drawing, I used the idea that a point here, a little bit removed from the axis, is at c plus some constant, and here we have c minus some constant. Now I'm just going to draw on top of that, but using a different kind of scaling that depends on n. Or I should have said this graph is in the limit n going to infinity. So here I use a different scaling where these points are just removed by constant divided by square root of n. Okay, so this kind of stretches the graph, and what we see then, and this is what I'm going to talk about, is that there is a nice transition that follows a Gaussian distribution, cumulative Gaussian distribution. Okay, so this curve has somehow the form the cumulative Gaussian distribution times now square root of n rate minus capacity, so around the rate is centered around the capacity, and here we have some other parameter that we want to find out about. Okay, so this is the behavior when you zoom in. Just as a kind of intuitive notion of this, we can see that this channel is used n times independently. Somehow the errors, well, you can see if the probability of being in a very bad kind of situation where all the channel uses turn out to be bad is the probability of being in this tail. So as long as you have a rate above that, then you will be in trouble. This is very rough, maybe not very helpful kind of understanding, but we are in an IID setting where somehow a central limit theorem or a version of that will apply. Okay. So now I need to introduce some additional notions to make this a bit more formal. So first of all, we have a code which is just given by a set of messages, an encoder that maps this set to our input set, and a decoder that maps the state, or this is a POVM general, maps the state to, again, to the message set. Okay, and we can kind of see this as a Markov chain where we first have the message, apply the encoder to get the input, then the channel, and so here this is what I call rho bx, then the decoder to get again an estimate of the message. And the quantity non-asymptotically that we are interested in, okay, I should say that the size of a code is just the cardinality of the message set. So now the quantity I'm interested in is what we call the one-shot fundamental limit for a probability of error epsilon, which is just the maximum m, where m is a natural number, so that there exists a code of size m such that the probability of error is smaller than epsilon. Okay, and these random variables somehow follow from this construction here for a fixed code. I mean the distributions of this. Okay, and so this is a quantity that is valid for, or that you can define for any channel. In particular, we are interested in n memoryless repetitions of a channel. So the task is to characterize m star of Wn epsilons for large n. Okay, and this just denotes n-fold memoryless repetition of the channel. Now, using this kind of quantity, we can describe what is already known. So first, the HSW theorem with the weak converse. It essentially tells us that the following. So we take the limit n going to infinity of 1 over n log of this fundamental, of this one-shot fundamental limit. This nomenclature is actually due to Polyansky. I think he calls it that in the classical setting. So we look at this limit and we see that this is the capacity. Now, why is this a weak converse? The weakness is in this additional limit epsilon to the 0 that we need to take. Because the strong converse tells us that that this holds without taking this limit. So we don't need this limit anymore, and otherwise it's the same. Which means that the capacity is for all values of the error between 0 and 1, the capacity is going to be the same. Okay, and so this was shown by Andreas Winter and also by Ogawa and Nagaoka. And what they actually showed is something slightly stronger than just this statement. They actually showed that if we look just now, not taking the limit, but looking at an asymptotic expansion of this quantity, they showed that I don't need the 1 over n here. So they showed that this quantity grows as n times the capacity, and the second order term grows as at most as square root of n. Okay, and this kind of relation also follows from the strong converse proofs. For the strong converse proof that Mark was talking about last week. We actually know how fast this one grows. And the goal of this talk now is to find out more about what is really going on here. Okay, so now I need some more definitions first. That is unavoidable. So first of all, in this setting we can define a state a classical quantum state that is somehow induced by the probability distribution here on X, which is just given as this. So it's this classical register that is correlated with the output state of the channel. And using this we can define the mutual information. So this is just the divergence between this state and its marginals. This is one way of writing the divergence, the mutual information, and an alternative way is just to write it like this, where we take an expectation value over X, and here we have the one particular state of the ensemble, and here we have the ensemble average. Okay, I'm writing these two different definitions down because I'll use them both. And so d rho sigma is the usual quantum relative entropy or divergence. Okay, so with this mutual information, we know how to define the whole capacity, and so that the capacity of the channel is then just the maximum over all probability distribution on X. This mutual information. And again, an alternative way of writing this that we've already seen last week is as a radius of divergence radius. So then it would be a minimum over states on the output space and a maximization over inputs. And here we have kind of a distance, the divergence between the output state and this divergence center, sigma b. Okay, so now we have these quantities. Now one set that is particularly important is the set of all probability distributions that actually achieve this maximum. These are relevant because they will tell us, they will allow us to define the second order term, which we do next. So for this, I first need to extend this notion here. So the relative entropy can be seen, at least if you think of these as classical distributions. This is the log likelihood ratio here, and what we're looking at is the expectation value over the log likelihood ratio. And then one could ask, what is the variance of this log likelihood ratio? And one can come up with one of many quantum generalizations of this. Obviously, that doesn't tell us whether it's the right one, but the results here indicate that it probably is. So then we just have this difference. Sorry, this is a bit tight here. Minus the divergence, so minus the expectation squared. So the expectation of this variation squared. So this is kind of the most straightforward way one could define this variance. It turns out to be the right one for this problem. So now one can, similar to the definition of the mutual information, one can define a mutual information variance. But now this will actually, I'm going to do that here. This can go in two ways because we have these two equivalent definitions here. It turns out that for the variance this is no longer the same. So we define two different quantities. This one would just be the information variance of this. So this is u, this is v, and here we just take this sum, this expectation value outside. And then one small lemma is to show that these two are actually equivalent for probability distributions that are in this set pi. But in general they're not. Okay, so but in this set they're equivalent, and we will actually use that because this quantity here appears very naturally in the direct part of the proof when we use random coding, whereas this one appears very naturally in the converse of the proof. So to show equivalence, we will actually need this. Okay, so now we have this. Then we can think of two quantities here. They tell us, or they evaluate the maximum of this of these quantities on the set pi. So we have maximum over p in pi, and then okay. The same we can do with the minimum. I'm not going to write it again. And what turns out to be really the quantity we are interested in the end is an epsilon dependent quantity which just evaluates to V min for epsilon smaller or equal to 1/2 and V max for epsilon larger than 1/2. This you will understand in a second when I get to the next part. So okay, so now we have the definitions in place that we need to state the main result. Is there anything? Oh, yeah. So the main result is that this log n star Wn epsilon has the following expansion up to second order. So we have n times the capacity plus square root n times this epsilon. This is called channel dispersion in the classical literature. Times the inverse Gaussian distribution plus some terms that are growing slower than square root of n. In fact, for the achievability, we can show that this is indeed as in the classical counterpart. This is growing logarithmically in n at most. Here, for the converse, we can't currently show that. It's also, there are classical channels for which it is not true, so one could only show it for a particular class of channels. Okay, but this is what we have now. So we fixed the second order term, and beyond that we don't know exactly what's going on. So what does this mean in terms of a plot? So this is slightly different plot where I have the capacity here, and this is the number of channel uses, and a very practical question one could ask is how large does n need to be so that we can achieve or get close to capacity. So what is on this axis is the rate, and this approximation here says that okay, we're gonna approach this capacity in some way described by this Gaussian approximation, but this is only an asymptotic result. So now one question is, for particular channels, is this a good approximation of the behavior for small n? And at least classically there are channels for which this has been shown. So there will be the binary symmetric channel and the binary erasure channel, because for those one can actually calculate the non-asymptotic bounds numerically for even for large n. And for those it's known that the converse bound and the direct bound somehow sandwich this curve here. So this seems to be, at least for those channels, a very good approximation. But in general, this is actually not really understood. So for general channels, one has the asymptotics, but one doesn't really know what's going on in between. What one can see, though, in this kind of graph is that most previous approaches to the strong converse, for example using Renyi divergences, they will actually give a curve like this. So the converse bound will approach the capacity from above. This kind of analysis, at least for very large n, will give something that a converse bound that goes below the capacity. So for all channels, right? Because we know that in the second order we get to this curve.
Can you explain the significance of that?
So this one is always staying above capacity. Just by the techniques don't allow anything beyond that. Whereas this kind of bounds, I mean, the ones that one can evaluate for finite n, they will give something that goes below capacity at some point. It's just that at the moment the constants are quite bad, so I drew it in a way that makes it worse than the other converse bounds for small n, which I don't really know. The only thing I know is that at some point it will be better. Okay. And for quantum channels, actually, my guess is that the similar behavior appears for very symmetric and nice channels, for which one can evaluate the non-asymptotic bounds. Well, in fact, Will has done it for one channel more or less. I mean, yeah, I mean you have a curve that for a converse bound that looks very similar to this, at least. Okay. So now still have half an hour to go into the proof, but I will not be able to present the proof in its full glory. So there will be a lot of shortcuts in that.
Especially in the classical case. I mean, what you showed, I know where this comes from and so on, and the idea of it being sandwiched, but the bound that you get for the second order asymptotics there seems to also have similar. I mean, it has a lot of constants buried away in it, and would it also give? I mean, does it also give a similar kind of poor low end behavior like you showed for the classical one?
Oh, this one?
Yeah.
No, that was for the quantum one. Although for the classical one, I think the same
That's what I was wondering. It's
Yeah, yeah.
kind of still the same story, really. But I guess there's a little bit better because you've got more control on the third order term. But well, actually,
But that one
even
actually
that,
doesn't
it
matter.
still depends on the constants, right? Okay.
Yeah. It's more the fact that the Berry-Essen theorem that we use to derive these bounds at some point doesn't behave very well for small n, and that is kind of what destroys these bounds. So yeah, I mean, one solution might be to use more or better specialized Berry-Essen theorems for certain channels. That will give better approximations. But I think we're still a bit away from the point where people really want to have the finite n capacity for a certain for certain channels for practical applications. Okay, so I'll go a little bit into the proof. And there are essentially two main ingredients. One of them is one-shot bounds. And these are just bounds on this m star quantity for general channels. These were mostly known before, so I'll just cite the literature. And the second ingredient is and these are given in terms of a quantity known from hypothesis testing that I'm going to define on the next page. And then we need the asymptotics of this quantity. Okay.
Marco? You commented about the converse bounds, how it sort of comes in to play for larger n. What about the achievability bound? Is there a similar thing happening, or does it come into play for all n?
No, it's the same.
It's the same kind of approximation. Okay.
I mean, it's as soon as you want to approximate this Gaussian, this nice curve that is made by this Gaussian approximation here, you get into that problem, because you need to show that whatever your distribution is in the ID case, you have some sum of random variables. And we'll see that actually in
Okay, so it's the same issue with the Berry-Essen theorem.
yeah. Okay, so I start with the one-shot bounds, and there one very useful bound. Okay, there's something missing. Okay. So one very useful bound for the achievability states that this quantity here is always larger than again a maximization over distributions of this non-asymptotic divergence evaluated for the state, for the usual state. Now there are many different ways of writing this. Okay, minus some term that becomes small very quickly when we look at large channels. So the reason I write it like this is because this should remind you of the one way of defining the capacity, just that now this divergence has been replaced by a non-asymptotic version of it. And this one here is defined as for now general states. In this way, where this beta is the minimal error of the second kind, when the error of the first kind is fixed to be smaller than epsilon. So this is really just a hypothesis testing problem where you can choose the measurement operator Q. You have two types of error. One of them has to be larger than smaller than epsilon, the other one should be minimized. So this very natural quantity. From this we can define a divergence. This normalization here is just due to the fact that we want this to be always positive. Okay, so one argument is that this somehow describes the non-asymptotic behavior of this M star. And to make this argument more complete, we would also need an upper bound on this, a converse bound. I should say that this kind of bound is essentially due to Wang and Renner, and they based it on Hayashi Nagaoka's results for classical quantum channel coding. The converse bound is as follows, and here there are different ways of phrasing this again, but the way we chose is somehow very closely related to this divergence radius formulation. So we have a minimum over output states maximum over inputs and then exactly the same as in the asymptotics, plus some small term. Okay, and this bound is very closely related to many things. The classical results, the meta-converse by Polyansky et al., Wang-Renner's results on the converse, and also Matthew's results. They're all in the same spirit. So this is just one way of formulating this. And yeah, the reason why I find this one nice is because it looks like the asymptotic bound in some ways. Now one can evaluate these for n uses of the channel, and because I will need that later, I'll just write that down and simplify it a bit. So since for the achievability we are free to choose this probability distribution, for n uses of the channel we just restrict ourselves right now to product distributions. And we also choose these small parameters here that somehow deviate from epsilon. We choose them to be 1 over square root of n. That will later turn out to be very useful. Actually, it's already clear now why that's useful. So if we have here a deviation that grows as 1 over square root of n, then by continuity we can just take that out and it will only add to the constant term here. So choosing these constant or these deviations to be 1 over squared of n is a useful choice. And we also see that this choice on this logarithmic term will give us a contribution that is logarithmically in n.
So epsilon is not is lower bounded by an n-dependent term, right? Because you want that exponent to be positive. Epsilon minus 1 over square root of n.
I will just take n's that are large enough so that this is true. Yeah, this is one limitation we have on n. Yes. So yeah, I should say that n large enough. Okay, so here I just have a product distribution now. And here's something that scales logarithmically in n, and I'm just going to ignore for now. So this is a lower bound on m star, and an upper bound we can get by now minimizing over all states on this n-fold product space. This will be simplified later. A maximization of vectors of length n of input symbols. And here we have plus 1 over square root of n. Okay, and again a logarithmic term. Yeah, so these bounds are nice and good, but obviously we don't know really how to calculate these things. So now we have to use asymptotics. And these were actually derived by KV and also by myself and Masahito Hayashi. For this divergence, and I'm not going to go into too much of the detail here, but I will try to justify why these are the right, or why this works. Can you all see this part? Okay. So the result is that I will try to use is that this quantity here for some arbitrary product state on the first system and an ID state on the second system, that this evaluates to well, this is kind of the expectation of this quantity, in some sense, plus the second part, which is this variance term. And some logarithmic contributions. Okay, so now this part either you can just well, you will have to believe me that this is the case, but I can somehow justify it at least in the classical case, where I'm just looking at two distributions here, and then it's known from the results by Newman and Persson that this hypothesis test can be, or is closely related to the log likelihood ratios of the two distributions, and in fact one can formally show that, well, let's do it right in the, no, okay. So for arbitrary distributions, this quantity is related to the following. Which I'll explain once it's written down. Okay. No. So we have x distributed according to p, and then we're looking at the tail of this distribution of the log likelihood ratio. So this just is essentially an inverse. So we're looking at the R for which the probability, the log likelihood ratio being smaller is most epsilon. So if this is kind of the alphabet and the events are ordered so that the higher log likelihood ratio get over here, then we're just cutting off at epsilon. Okay, and these two things are very closely related, hypothesis testing and this log likelihood ratio, or this distribution of the log likelihood ratio. And now you can kind of hopefully already see what's going to happen.
It's like the dual formulation in the quantum test?
No, it's the maybe one can show something like this using the dual, but I don't think so necessarily. No, it's just known classically what the optimal test is, and if you write it down, you essentially immediately find this
I just thought
relation.
that maybe you can make the same conclusion precise also by, because I thought it was like related to its optimality conditions for the, that's related by known difference. But maybe
We can discuss this later. Maybe I don't know. It might be interesting to explore. Yes. In the quantum case, it's not so clear what this quantity here actually is. So I think this was a quantum extension of this was defined by Nagaoka and Hayashi, I think, that we also use, but it's per se it's not so clear what one would take here. Okay, so now we're looking at this for this particular case here, where we have product distribution and an IID distribution. So what will happen here is that here we have a logarithm, so this will actually turn into a sum of the different log likelihood ratios of the different instances of the channel use. And this is also a product distribution that we're using to evaluate this. So we are in the setting of the law of large numbers, or the central limit theorem, and that's how the Berry-Essen theorem gets into play. If one just applies it there and rewrites a little bit, one gets this form. I'm not going to do that here. Okay. So now it remains to somehow put these things together. So we have the the one-shot bounds here and this asymptotic expansion. Okay. So we've seen this this bound for the direct part. It's quite simple how to apply this now. We can essentially just directly do it. And since here in the direct part also the first state is ID, we can immediately, or we get an equivalent term, so this is this one plus the square root term as expected. And now we just observe that we can obviously still choose this distribution, so we choose it on pi. Then we have here the n times the mutual information, and then we will, depending on epsilon, choose it to minimize or maximize v. So I didn't explain this before, I actually forgot. So we define this v as a function of epsilon, either the maximum for I think the minimum for epsilon smaller than 1/2 and maximum for epsilon larger than 1/2, and this is exactly where this function here changes sign. So this looks like this. So at epsilon equals 1/2, it changes sign, and now obviously to have the maximum throughput through the channel for epsilon smaller than 1/2, we want to minimize this dispersion. For epsilon larger than 1/2, we want to maximize it. So this is one observation that one can make here, is that it actually for finite block lengths, it makes a difference which capacity achieving input distribution we take. Okay, and so if you do that, then it's immediately clear that we get the desired bound here. Okay, so now the converse is a bit more involved. I will just start and then see how far we get. So the first thing to do is to choose in this non-asymptotic bound. In this non-asymptotic bound, we still have a minimization over, here, a minimization over these states sigma, and we can just choose one state obviously here. The state I'm going to choose is very particular one, and it's so this converse proof is somehow uses the method of types, and in particular the fact that the number of types are growing polynomially in n and not exponentially in n. So I'll just explain what this is. So what I'm summing over, or what I'm yeah, so this is just a number of types of sequences of length n. I'm just writing them as probability distributions, it's just the empirical distribution of this type. And the state okay, so this is obviously an ID state, but we have a sum of such ID states, and then this is properly normalized again, and these are n types. Now, what are these things? So these states have the form, or these distributions have this form. So if we take any vector of length n of input symbols, then we can define a distribution for that. That just counts how many times each symbol appears and well, normalize it. So this is the empirical distribution of this vector of input symbols, and if we just take all of them together and put them in a set, then we see that the size of this set grows only polynomially in n. Okay, so we find this state, and now the converse bound is still a maximization over these sequences or these vectors. And now here, well, so here I'm gonna use some additional argument, because I don't really want to have this full state in there. And what I want to do is to pick for every of these vectors, I want to pick the particular distribution that I like, namely the one that corresponds to the empirical distribution of this xn. So this is what I will get, and I'll just tell you what kind of properties of this divergence I need to show this. So now I have this again this ID state. So what did I do here? First of all, I use the fact that if I have here, I started with something of the form divergence of rho, and here I had, let's say, alpha sigma 1 minus alpha tau. Then it's quite clear from the definition, if you look at it a bit more closely, that this can be lower bounded by just dh epsilon of rho, and here just alpha sigma. Okay, this state is smaller than this one. If you look at the definition, you see that such an inequality holds. And then the second step is just to say that this is the same as rho given rho with sigma, and then we get a penalty of log 1 over alpha. And this penalty here, this is why it's important that this only grows polynomially in n, because this is going to be the alpha. Okay, but this O log n term eats up all these tricks. So now we're at this point with this state. Yeah, I'm almost there. Okay, so I'll make this short. Now at this point we can obviously apply directly the asymptotic expansion again. The result is slightly different in that this term will get to be a sum over of divergences and this is going to be the average state, but now the observation is just that this can be written as a mutual information if I take here again the empirical distribution over inputs. And this is now using the, I don't know whether they're still here, one of the definitions of the divergence, namely the one where you take an average over x and then evaluate it. So if you look at this one and just insert here the empirical distribution, then you see that this is equivalent. A similar thing happens with the second order term, and at that point you can just replace this maximization over empirical or over vectors by maximization over all probability distributions, and then you're at the same place as for the direct part. Yeah, so that was a bit of a shortcut. There is yeah, I think I just so this would then show the converse, and with that the proof is kind of complete. Now there are several open questions that one might be interested in here. One of them is, so we know for other channels and for other kind of definitions of capacity that the strong converse holds. So also in these cases one might ask if one can also do a second order analysis of the problem. And one case where we are currently working on that is for just a classical capacity with product inputs or separable input states. But there are other questions where the same, where I would expect that the same also holds, maybe for an entanglement assisted capacity, for example.
That's exactly the one you studied. Classical capacity products is.
Yes, I mean, one has to be. It is very similar, obviously, but it's not the same. The problem is that the techniques we use for the converse, using this type counting, they don't apply anymore if you allow arbitrary product inputs. You can't just put them nicely into types. So essentially, technically what happens is that the set of inputs is no longer finite. So you have to be able to deal with like the set of pure states, for example. And so technically that's there is an additional challenge, but I think I'm quite confident we have solved that now. But for other problems we have currently no idea how to, or we have some ideas, but it seems to be very difficult to tackle the problem. Yes, another question is if this has any applications in other areas of physics, or if it might be already known in other areas. I don't think so. But yeah, I mean this kind of effect happens always when you go when you have in the limit some kind of Shannon or von Neumann entropy, and you want to know how fast you approach it. So I'm interested in other applications of this as well. Okay. They've all been asked during the talk as well.
I guess you didn't look at like quantum erasure channel or some of these basic channels.
To actually evaluate the bounds. No, I haven't really done that. But yeah, it might also be interesting to see how well the approximation performs towards these channels. Yeah.
Some comments, but maybe after the talk.
Okay.
Thank you very much.